The biggest problems facing humanity, climate change, incurable diseases, plastic waste choking our oceans, often feel like impossible puzzles. But what if a single scientific breakthrough could hold the key to solving them all? The solution wouldn't be found in towering machines or massive laboratories, but in something so small, so invisible to the naked eye, that it quietly exists in every living cell: proteins. And now, with the help of artificial intelligence, we've unlocked a way to read their secrets faster and more precisely than ever before. This breakthrough, called AlphaFold, is being hailed as one of the most useful accomplishments AI has ever achieved, and its ripple effects are only beginning. For decades, scientists struggled with what's known as the protein folding problem. Proteins, the microscopic machines that make life possible, don't just exist as straight chains of amino acids. They twist, curl and fold into complex 3D shapes, and that shape determines everything about how they function. Hemoglobin, for instance, is perfectly shaped to carry oxygen through your blood. But determining the structure of a single protein could take scientists years, sometimes even decades. The complexity of these molecular structures was compared to solving the biological version of Fermat's last theorem, one of the hardest puzzles in mathematics. To grasp the scale of the challenge, consider this. Over 60 years, tens of thousands of scientists worldwide managed to determine the structure of only about 150,000 proteins. Then AlphaFold came along and in just a few years solved the structure of over 200 million. That's practically every known protein in existence. It's as if humanity had been trying to piece together the world's largest jigsaw puzzle one piece at a time, only for AI to suddenly complete the entire picture overnight. So how did AlphaFold do it? To understand this, we need to look at the nature of proteins themselves. A protein begins as a simple string of amino acids, like beads on a necklace. Each amino acid has a central carbon atom, a pair of chemical groups on either side, and a unique side chain that determines its identity among 20 possible amino acids. These chains naturally react with one another, creating bonds, twists and folds that shape the final structure. The forces at play are mind-boggling. Hydrogen bonds, electrostatic attractions, solvent interactions, all pushing and pulling like an invisible dance. And yet, the final shape must be precise, because if a protein structure is wrong, it simply won't work. This is why scientists say proteins are like tiny machines. They must be perfectly built for their function. In the early days of protein research, scientists used painstaking experimental techniques to uncover these structures. The first major success came through a process called X-ray crystallography. British biochemist John Kendrew spent 12 years determining the structure of myoglobin, an oxygen-storing protein crucial to heart and muscle function. It wasn't easy. His first attempt using horse heart failed because the crystals were too small. Desperate for a better source, he ended up using whale meat, which finally gave him large enough crystals to analyze. His success earned him the 1962 Nobel Prize in Chemistry, but the process was so difficult and expensive that progress remained painfully slow. Even today, crystallizing a protein can cost tens of thousands of dollars and consume years of research. Scientists realized that a faster, cheaper approach was needed. If we could determine the 3D structure of a protein simply by looking at its amino acid sequence, we could bypass the laborious crystallization process. This idea sparked decades of computational research, but despite advances, no algorithm could predict protein folding with enough accuracy. The challenge was monumental. MIT biologist Cyrus Leventhal once calculated that a single short protein chain with 35 amino acids could fold in an astronomical number of ways, far more possibilities than the number of atoms in the universe. Even the fastest supercomputer would need longer than the age of the universe to check every configuration. The task seemed hopeless. Yet, as often happens in science, a competition changed everything. In 1994, Professor John Molt of the University of Maryland launched the CASP Challenge, where researchers would compete to build models that predict protein structures from sequences alone. At first, success was limited. Early models scored below 40 on a scale where 100 meant a perfect match. But the competition inspired innovation. One breakthrough came from David Baker's Rosetta algorithm, which combined global computation with distributed computing, enlisting idle home computers worldwide to process data. Then, something remarkable happened. Baker turned the challenge into a video game called Fold It, allowing everyday people to experiment with protein folding through an interactive puzzle interface. Within weeks, tens of thousands of gamers were participating, and their collective efforts actually solved critical problems in HIV research. One of those gamers was Demis Hassabis, a former chess prodigy and founder of DeepMind, the AI company that would later create AlphaFold. DeepMind had already made headlines with AlphaGo, the AI that stunned the world by defeating human champions at the ancient game of Go. Hassabis, however, had bigger ambitions. He believed AI could solve real scientific problems, starting with protein folding. Thus, AlphaFold was born,